all, again, thank you to Raul for the introduction, also to Diogo as well. So I'll be half chairing the opening sessions. There's a minor change to the schedule because this is my tool. So there was a minor change to the schedules because Havard Rui will be coming a little bit late, so he's going to be speaking for my slot, which is 1:30, and I'll be taking over at 10:30. So we're a little bit early, but I think it's okay. We can get moving now. So this first opening session is pretty much on data simulation / filtering, and our opening speaker for this session is Professor Ibrahim Hoteit, who's a professor in earth science and engineering, as well as applied mathematics and statistics, amongst others, and is, of course, the director of the KAUST, for the moment, KAUST Climate Change Center. And it's enough? Okay, all right. And I was hoping your title would be up here, so I didn't write it down. Okay, so please take it away. Yes.
Okay, working? Very good. I should share the screen. There's the screen. Okay. Okay, AJ, thank you very much. And thank you, Raul, for the opportunity. It's a pleasure. I come from the earth sciences and engineering. I'm applied mathematician by background, but now I'm all over the place. All what we do is actually now oriented toward building advanced machinery for forecasting and predicting short-term, long-term the circulation of the Red Sea and any applications that come with it. And we expanded lately to the Arabian Gulf. And we do not just look at the application, but everything we do is driven by application. Okay, and everything we think, we think in terms how we solve this problem. And this is what I'll try to give you a brief, a general overview of what we're trying to do. I put everything now, everything we do now under the Virtual Red Sea Initiative. In around 2016, when the word started to come up on the new projects, mega projects along the Red Sea coast, our PPR back then, Frechet, called us and asked us to put an initiative to start working on something that could support this application. And we came up with the idea, we called it Virtual Red Sea Initiative. It was about just developing tools and modeling, forecasting, design tools to study the Red Sea environment, okay, and predict its fate. And so we put together this machinery. I always start from this slide showing a comparison between a 1 kilometer model GCM, ocean GCM, compared to satellite sea surface temperatures. This is sea surface temperature for 1 year simulation, just to show you the level. We're not cheating here. There is no simulation. There is no data, just forward run. And don't think the satellite is also perfect. The model is not perfect, but satellite is not perfect either, especially along the coast. So satellite can get can see things that might not be true along the coast because of the bathymetry. But you see this intrusion of the water from the Gulf of Aden. It's called intrusion. We capture it super well. And you see also this complicated structures of eddies, vortices. It's a very, and this is what we're seeing on the surface. In depth, it's much more complicated as well. But we get the whole circulation really well without assimilation, and we use that to study the physics. We use that to study how the Red Sea functions and how this circulation drives its productivity. Very important for biology. And actually, usually I ask the people which one is model, which one is data, without even assimilation here. If I put assimilation there, you'll not see the difference. And what do you think? But which one is model, which one is data? Which one? No, the left one is model. It's higher resolution. We have a supercomputing facility here. We can solve more than what a satellite can see. Okay. So this one is models. This one is actually data. Okay. So when we put the virtual REDC initiative, we split it into 3 parts. After long discussion with the VPR office, we have short-term forecasting, and this is what I will be talking about today. Short-term forecasting is the 1 day, the 1 hour to the 2 weeks, 10 days, 2 weeks. Sub-seasonal to seasonal is from the 2 weeks to the 6 weeks. This is sub-seasonal, what we call, and seasonal is from the 1 month to the 6 months. And long-term projections. The first part is now sponsored by Aramco, and this is what I will be talking about today. It's all about short-term forecasting. The other 2 are now under the Climate Change Center, and this is exactly what we're doing as part of the new Climate Change Center with the Ministry of Environment. So I'll focus on this one today. And actually, it was when we designed it, it was we didn't think this way, but it ended up being very well designed because we built this machinery, and when the call came from the ministry and from Aramco, we were ready to answer it. So this is the machinery what we have put in place. So we have the whole system running. It usually doesn't happen in one group, but we have a big group now. So we have the ocean, as we have the atmosphere forcing the ocean and forcing the waves. And once we have the ocean and the atmosphere, we can do any transport, and including ecology. Okay, and we have now part of the virtual REDC initiative with Scripps Institution of Oceanography. We coupled ocean and atmosphere and waves fully coupled together, and we're working on the assimilation to the cup problem. But now they are fully coupled, and they are all driven by data. So whatever data we have, we assimilated data into these models. I'll focus today on the ocean component. Okay, and all this machinery is a very heavy machinery. So and they are all nested, so it's as realistic as it can get. So we go from the global models to regional, sub-regional, all the way to the scales, and this is a scale of 100 meters to NEOM, and we go also to the 20, 30 meters resolution scales, but we have to reduce the domain every time because the computing becomes too heavy. But it's all nested, and the boundaries are realistic, whether it's from the ocean or from the atmosphere. Just to give you an idea, we're solving the full Navier-Stokes equation. So they are very, very heavy models. And again, everything we do, we have to keep in mind that these models are quite heavy to run. In the Red Sea, the dimension of the stage just from discretization at 1 kilometer is around 10 to the 7, 10 to the 8, 10 to the 8. And with the new machine, we're going to the 500 meters, and you will multiply this by around 8. So we're getting to the 10 to the 9 with the new supercomputing coming soon. And these are the type of data we use. We heavily rely on satellite data because they give us a very nice full coverage of the surface. But we also we have a project now, and Aramco is deploying 6 radars that give you coverage of the half of the Arabian Gulf on the surface in terms of velocity, radial velocities. So this will be also assimilating these. Our ships data, we use Argos log data, unmanned vehicle data, whatever data available, we can digest it, we can assimilate it. And to give you an example of the data that have been collected in the Red Sea in the last years since KAUST started, you see that is heavily tilted towards the East Coast because it's all mostly KAUST, 90%. Before that, there was nothing almost. And something missing is the African side. This is the international water where we can go. So we heavily cover our side, not the other side, except you see these 2 floats, like for instance, they float with the currents, so we cannot control them. And we should use more of these because we cannot control them, so we can go to the other side. Otherwise, there is no way for us to go to the other side. But the issue with that, last month we lost $270,000 float because it floats and it got stuck in a mountain or something undersea, and we lost it. So this is the danger of using these floats. Okay, so to go to something that you guys are more familiar with, this is how we model the system, state space model, and you are more familiar with this than me. So for this is the dynamic of the ocean models, atmospheric model we use. it represents the ocean model, and we model it as a stochastic. There is some noise, there is some model error that we cannot, we do not know well. So we model it as a random noise. And so basically, if I know the state of the ocean now, I use my machinery, my ocean model, general circulation model, primitive equations, to integrate it and compute my ocean state at the next time. Okay. And the observations, they can be linear, nonlinear, and these are the observations wherever observed, and they are function of the state. The state of the ocean includes temperature, salinity, velocities, and sea surface height. These are the prognostic variables from which I can derive all the other ocean variables. And the observations also are noisy, so we put them also. We add a noise in here. Again, when we describe the system, the dimension of the state is around, in our case, 10 to the 8. And so to estimate the state of this state space model, since it's stochastic, we compute the probability distribution to characterize the state. We try to compute the probability distribution of the state given all the available data, and we solve it sequentially, what we call sequentially, or in a filtering sense. So once the data become available, we compute the probability of the state given all previous data. And then this is what we call analysis. When we don't have data, we forecast with the model, but we don't forecast the state, we forecast the probability distribution of the state. And we wait till we get a new observation. So basically, the way it works, so we start from probability distribution, we integrate it with the model. Again, don't forget, we're using the general circulation model to integrate a PDF in a dimension 10 to the 8 to make a forecast probability distribution. And when we get the observation, we update the forecasted, we call it forecasted PDF, with the data using bias rule, posterior, just it's the product of the prior, the prior is a forecast now, and the likelihood, and then we get an updated probability distribution that we integrate forward. So it's all sequential, one after the other. Every time we get data, and it fits very well in our ocean forecasting framework. We want to forecast the ocean state given the data every time. So we want the conditions of forecast on the data. Okay. And these are our Holy equations. The forecast step, we are integrating a PDF forward in time. This is a Kolmogorov equation. And then there is another step, which is the bias, the regular bias inversion rule. So the prior for us is every time is the forecast of the previous state. This is a filtering framework. Okay, and we have to solve these equations with this general circulation ocean model, and it's very heavy. So the first thing we do, we have to discretize the probability distribution in order to find some numerical solution to this problem. There is, of course, no analytical solution. And there are different ways that have been proposed to discretize the probability distribution. There are the most common in our community we assume it's Gaussian, simply. So if you linearize the Navier-Stokes equations, the primitive equations, and you assume like Gaussian likelihood, everything becomes Gaussian, and you come to the Kalman framework. There are what we call, if you use Dirac mixture or point mass approximation, just frequencies, this is what the particle filtering approach. There are a lot of research in our community to see if we can apply the particle filtering framework to our large dimensional problems. I'm not a big fan of these, just because in a 10 to the 8th dimension, although this numerical dimension it should be much smaller than the physical dimension of the problem, but still, we should be very ambitious if we think that we can approximate a PDF of this large dimension by a small number of particles. I think it's much more efficient, and we should be more programmatic, maybe to think in terms of few Gaussian mixtures, depending on the number of particles we can use. And this is the Gaussian mixture. The third one is the Gaussian mixture approach. And there's a combination of these, which discretization we use in terms of on the forecast step and on the analysis step. I'll The most popular of which is, I think you already heard about the ensemble Kalman filtering, and it's a mix of Dirac mixture as a forecast step. So as a forecast step, I have a bunch of particles representing the uncertainties in the initial conditions. I just integrate them all forward in time. And the word ensemble is just a nice word to say I'm using a small number of particles. But it became a very popular word. So I have a bunch of particles as the initial conditions. I integrate them with the ocean model forward in time. So if an ocean model takes, depending how long I run it, it might take from several hours. For a few days, it takes now on Shaheen for 2 kilometers around 3 hours now. We brought it down. But I need to run massively all the ocean models at the same time or one after the other. If I run them one after the other for each member, it will take forever. So we run them all at the same time, and it takes a lot of Shaheen time. So I get a forecast ensemble from this. It's very simple, very straight. And then this forecast ensemble, since even if I started from a Gaussian distribution, even if the particles are sampled from a Gaussian distribution, when I get to the forecast, the distribution, because of the model, the Navier-Stokes are nonlinear, I get to a non-Gaussian distribution. And here's the word Kalman comes from. I assume it's a Gaussian. So basically, we're looking for the best linear unbiased estimator in here, if you want. And then once I assume it's Gaussian, I get to a Kalman update. And there are a lot of flavors of ensemble Kalman filtering trying to match this Kalman update. There are what we call deterministic ENKFs, where we exactly match the mean and the covariance right away. And then we come back, and then we need to resample, and the resampling is deterministic. So the resampling is not stochastic in general, it's just we're trying to match a mean and a covariance analytically. And there is a stochastic ENKF where we perturb the observation, and there is a random perturbations. And actually, we have some studies in there, and the stochastic ENKF in general is better. The only issue is that if you have a small ensemble, and that, depending on the small ensemble with respect to the number of observations, you're not resolving the rank of the observational error. We can talk about this later. So if you resolve the rank of the observational error covariance, then stochastic, random sampling we beat easily these deterministic ENKF. But if you go to our community, if you're using stochastic ENKFs, they will shoot you right away. Oh, we know it doesn't work with small ensembles in the hundreds that we use in our dimension. Anyway, this is the state of the art in our operational systems. So we use that now for ocean forecasting, and I'll show you the system we have. And because there are many other uncertainties in the system, we used to use the simplest, most naive way of accounting for the uncertainties that we are missing in the system, because we don't know the model errors, there are other errors somewhere. We just inflate the covariance to say there are uncertainties that we are not accounting for. We just multiply the covariance by a small number, 1.0 something, and trial and error, we get a number. There are many studies trying to adapt this inflation factor, but the easiest and the most efficient was to tune it. This is what we used to do. But now there are other ways to account for other uncertainties in the system. The most important of which are the atmospheric forcing, the boundaries, and the internal physics. And so what we notice that just inflating naively can create some problems in the dynamical consistency in the initial conditions. So when we started putting these, using more realistic uncertainties in the system, and we use it for the atmospheric forcing, we get it from ECMWF now. ECMWF give us 50 members of atmospheric forecast. And this 50 members of atmospheric forecast allows me to do 50, to include uncertainties in the atmospheric fields and boundaries as well. But in the Red Sea, the boundaries are not very important. We put the boundaries outside in the Gulf of Aden. It doesn't affect the Red Sea, only at the seasonal level, not as a short scale. For now, we're not using, till now, the ocean global fields models, they also do not give, say, I'm not running ensembles yet. The atmosphere are more advanced than the ocean in the community. But in any case, in the Red Sea, it's not a big problem. And we also, to account for uncertainties in the physics, we perturb the schemes we use different schemes, and we're using also different parameters in the schemes. Okay, so we choose the schemes randomly, and we choose some of the parameters randomly, and we run them to include uncertainties in the system. So, and with that, we avoid any inflation, and physically, it's the solution is much better. So if we use inflation with 20 members compared to inflation with 50 members, you see the more you use members, the more you think you expect the correlations to be localized, which is a good thing. You know, we know when the ensemble is small, there is some low rank problems which means that one observation at a place in this area will have updates in the Gulf Eden, which we don't expect that. We don't want to do that linearly. And when you put perturbation in the atmosphere, the correlation become much smoother and much physical, but still there are long range correlations. And when we put perturbations in the physics as well, then we have even more smoother correlation. We usually like, we have a smooth update, but the correlations are long. When we put these uncertainties from the atmospheres that are low rank, they are projecting on the on low rank ocean ensemble, and we have to apply some tapering. I'm sure you heard about that. We call it localization in our jargon. So we restrict the update to the neighborhood of the observation. Okay, and once we do that, things work pretty well. And even with here, we run 100 members. We assimilate data, forecast, analysis, and Aviso, the best sea surface height product. And this is the data from TMI for the sea surface temperature in the Red Sea. You know, anything on the coast, we don't trust it very well, so remove it. And we get a very nice sea surface height forecast and analysis as updates, and we have a much higher resolution than the satellite product itself. So the machinery works really well with that. Probably you have seen this movie. I've been using it for 6 years. We should update it now, but we also do some visualization, try to be able to visualize the uncertainties that we get from the system. These are very large data sets. We have 100 ensemble members over several years. We ran it recently for 20 years, assimilating all data to create our own reanalysis for the Red Sea. And if you want to visualize that with 100 members, it becomes very, very complicated. We're trying to develop some machinery with GPUs where you can visualize the uncertainties in real time just by moving the mouse, and you see the distribution that we get on the side. Or you do some risk analysis. If I wanna, right now here, if I wanna pump some water from the Red Sea at a location, which locations are, let's say, I'm looking to build a resort, and I want the areas of the Red Sea where the water is always less than, the sea level is always less than 20 centimeters, let's say. So just by doing it, by moving the mouse, you can see over the time which are the areas where I can build my resort or not. And the glitches are the uncertainties on my instance. Now, we were the first to run 5,000 ensemble members with real ocean. And we ran that, but we didn't learn much, actually. But it was a huge effort. I'm showing you here just experiments, results from 250 members and 500 members, just to show you at 250, around 250, in terms of correlations, linear correlation is enough for the real ocean. Okay, so what we found is that the correlations are not improving beyond 100, 200 is more than enough to get the second moment, even in such a large dimension. So when we compare the correlation between 250 members, if I only use inflation for uncertainties, atmospheric ensemble perturbation, physics perturbations, again, they don't change much. But even if we were hoping that if we go to large ensembles, the correlations will become more local, as we used to see with inflation, but we didn't. And this is because the low rank of the atmosphere, uncertainties in the atmosphere are projected on the ocean. So we still need tapering, even if we go to very large ensembles. So the hope that we can drop localization with more members. Now we're not getting any advantage of using large ensembles in terms of localization. So localization is still needed. The other thing we saw from going to large ensembles is that the distributions became we're starting to have bimodality in the system because of the perturbation in the physics. You're using different schemes, and there are biases in terms here temperature. So we're trying to have bimodality in there, and we're still using a Gaussian distribution. So the correlations, these bimodal correlations between north and south, appear strongly, and we are using a linear Kalman update, which might not be optimal. So everything, any benefit we're getting from these large ensembles because of our restricted framework to ensemble Kalman filtering is lost. And at 100, 200 members is good enough. You don't need to go and spend more computing in there, unless you go and start doing some non-Gaussian updates to see if you can gain from these large ensembles. So we had a lot of work on Gaussian mixtures, but they are all on simple models, and now we have a postdoc hoping that we'll be able to try this machinery on the real ocean. So this is the state of the system so far in there. And so 2018, I'm telling you how things happened, and 2019 was a year that was important for us. And what happened is that there was a lot of geopolitical instabilities in the region, and we started seeing, and this reflected by many ocean spills that happened in the region. And we were very busy during this 2019. There was this oil spill, so we were supporting Aramco, but we're doing everything oil spill forecast by hand. So this is May 2019, June 2019, March 2020, and the biggest one, October 2019. It's this Sabiti oil spill event that happened in our backyard in Jeddah. Supposedly, there was an Iranian tanker that got hit by a missile, and it leaked oil, and it's just outside. And in Saudi, there was a lot of concerns that this oil will arrive to the desalination facility of Jeddah, and if this happens, it's a catastrophe because you have 6-7 million people without water. So we were working night and day with the ministry and Aramco to forecast the fate of the oil and to see how they can protect. There were many ships waiting for the forecast to see how to deploy. They can use some chemicals. They spray on the oil to make it sink, and they can use booms to protect the sensitive areas from the forecast. But they need a forecast with as much lead time as possible so they can prepare. And this is what we were doing. So 2019, we did this exercise, and these are we were processing real-time satellite images that were coming. This is what we get from satellites, images. When we process them, this is the oil we can see from satellites. And this is on the first day, the red. And the oil track on the first day shows that the ship actually, it was leaking and it was sailing, which should not happen. What's happening is just they opened the leak and they started sailing. And actually they didn't stop here 200 kilometers, they stopped somewhere here. So they were leaking while sailing. And this is against the rules. When something happens, you should stop and call for emergency to contain it. But here, you're just surrounding all Jeddah and the south with oil everywhere. Knowing that the circulation with eddies, and I will show you now, can move around, it can hit everywhere. There is no way to stop it. So on red, the first day, we had an image covering this area. So that's why we didn't see it down. The second day, in blue, and you see it started turning, rotating. And this is with the eddies I was talking about. Third day, we get two images. We merge them, we get the green. And the fourth day, we get the other extent from down. Okay, so we were taking these images and we're forecasting real time what's going on. To do that, it used to take us 15 hours every day to send. We send at night, at around midnight, the forecast to the ministry. And this movie got us $6 million. Because with that, we didn't exactly get it everywhere, where the oil hit, but we get it right on time. And they were very happy. So they came and they told us, okay, we want everything operational now. And this is where we get the money. So we made it fully operational. I can show you quickly. If I go to a web page, you still see the screen? Okay. how the system works. So we have two systems now. We expanded also. We have another system for the Arabian Gulf. They wanted both, actually. So here we have the backbone of the system, what I would call ocean atmosphere waves forecasted every night on the supercomputing. Every night the machinery wakes up, global data from a forecast, a global forecast, real data coming in. We can see ocean atmosphere waves. All the data are available in real time and accessible. Currents, you know, and these are all 3D available. Once, if there is an oil, now Aramco can go online, or the ministry put the parameters of the oil, where it happened, at what time, how much oil was released, and submit. We get the query. It takes 3-4 minutes now online, and anyone can do it, and then you can visualize real time also the fate of the oil, how much, predict how much evaporated, how much in the column, and we are updating the system to make it 3D visualization so we can see what's happening in the column as well. But we realize also that the machinery we developed can handle much more applications. Usually to do that, you know, you need to go to ocean group to get the ocean forecast. You need to go to atmosphere group. You need to go do the wave groups, put these data together, different format. It might take hours and days to do such a thing. Once you have everything in place, you can do it in a few minutes. And then, so we now with NEOM, we're doing energy forecasting, wind energy, solar energy. There are many applications. We're going to add soon radioactivity, search and rescue. And there are very interesting questions that we'd love to work with anyone interested in here. Like, for instance, I want to go from this location to this location under uncertainty, and I want to do it real time. You know, for shipping, for search and rescue, there are many applications like this. And the trick is to do it under uncertainties in real time. Okay, so these are the machinery we are developing. We're trying to push it. Actually, not we're trying. We're gonna push it sooner. Now the system is working. We're gonna push it real time. As we couple the system with another project with Aramco for real time detection of oil, all the way from satellite images. It goes to the operational system and it forecasts all real time without any intervention. And you get that there is oil spill, and this is the forecast. No need for anyone to intervene. And so the system is working on the back, and we're trying to make it, we're going to make it operational in the next month or so. The other thing we're going to push soon is also to put booms. So you can go online, put booms where to protect some areas and see what's going to happen. So, but then another question would be, what is the best location of the booms and optimization? This is more difficult. I don't know how to do it. And if you want to do that in terms of uncertainty, it becomes even more complicated, and we want to do it real time. But now we are allowing the option. I can put booms. I want to put booms. If I put them here, what would happen? So someone can do it by hand, put booms, push the button, forecast. It forecasts and tell you if this deployment is useful, is good or not for what I want to protect. Okay, if you can do it in optimization sense, that would be super nice. Okay. This is the state of the system now, and we are trying to enhance it in more capabilities and in terms of performances. Okay, I'll talk a little bit in terms of capabilities. Add more capabilities, as I said, and this will happen soon. Forecasting energy, air pollution in the same way we're doing transport, in the same way we're doing oil spill, radioactivity, early warning system for coral reefs, bleaching. How you feel, you know, there are many things you can apply. And one thing we wanted to use also is explore the uncertainty we have in the system. What I showed you, the forecast is one forecast, deterministic, based on the mean of the ensemble. But what we noticed is in the Red Sea, especially in the Red Sea, you know, these are two ensembles of currents that we get from the system. And the difference is basically mostly is this gyre is shifted up and down. And this is because of the data we don't have enough data to constrain the whole process. There is uncertainties in the currents. And with the uncertainties in the current, you'll see just a small shift in the vortex, in the gyre, in the eddy, you will forecast the oil in a different place, and this is problematic, and we cannot do anything about it. They are, once you go to this what we call mesoscale, and even with high resolution system mesoscale, they are not constrained enough by the data, and the uncertainties are large. And you have to account for this. You cannot tell the guys the oil is going this way and they prepare in another way. Also, you're not that far, but it can be quite far. So we want to account for the uncertainties in these currents when we do the forecast of the oil. So we started with a simple problem, passive tracers. So if I have particles, I want to forecast where the particles will go under the currents, ensemble of currents. So every particle, you run it with the ensemble of currents. The issue here is that since we're doing sequential assimilation and you're reshuffling the ensemble every time, the number of particles will quickly exponentially increase. So to avoid that, we just bin them. So we bin them and we resample according to the weights in every bin. So it depends how many particles gets into this bin. It has this particle, we put them in one particle with a weight, and from there we run again. So we keep the same number of particles over time, but we had to make sure that we preserve at least the variance. Otherwise, if we do that and we sample every time, we start choosing also the variance of the particles, and the probabilities get diffused. Kind of, yes, more or less, yes. But here, yeah, and we're sampling just from the first 2 moments here. And we get pathways, these are probabilities, and we get a probability map from this. And we can do it real time with the GPUs. So we had this smart, Thomas, very smart student. You can just click and you see where the particles go over 2 weeks. And after 2 weeks, you will see that in the Red Sea after 2 weeks, I cannot tell you where the particle will go. It can go to the right or the left. We'll take a point in the Red Sea, in the north. And just by clicking, you will see that it ends up in 2 different directions after 2 weeks. Okay, and this is much, we're accounting for uncertainties, and it's a better information for the people than telling them this is where it's going. We did the same machinery backward with Samah as well, and we developed it further. This is actually where we introduced the resampling. We match the variance in the resampling, and we can do it backward as well because it's passive tracers. You can run it backward. So if you use 100 uncertainties and artificially we reduced it to 25%, the source is here. We go backward and you see it points to 2 different locations, the distribution. But if we reduce the uncertainties in our current uncertainties to 25%, if you have more data, we can recover the source, which is pretty cool. But this is just forward, and backward we can do backward. We applied the same machinery to this oil spill system I showed you, and this is our assimilated product at 4 kilometers here, trying to represent the uncertainties in the forecast, and you see we're almost there. There are still, the uncertainties are showing more or less around. Is much better than what is the global product, deterministic global product is available. But we have this machinery now, and also it allows us, because we have the real satellite images, to see if our uncertainties are representative of what we're seeing really on the field. And this we will push this also soon into the system. We want to forecast probabilistically, but we have work to do to educate the end user from the other side. These are probabilistic forecasts. These are not deterministic forecasts. They don't like probabilistic uncertainties words. They like the word scenario. They are okay with the word scenarios. They are not okay with an word uncertainty. They don't like uncertainties. Okay, we're trying to push also, to do more capabilities in the system. Samah is doing his PhD on the backward problem. So sometimes we see some oil, and it happened 2 weeks ago. There was some oil, and there was a big dispute where the oil came from in the Gulf. And here we were doing it. Okay, we have satellite images of oil, And we want to see where the oil comes from. But with oil, you know, it's particles. We do it with Lagrangian particles, but it has weathering phenomena, beaching, evaporation, emulsification with the waves. If you put these, you cannot go backward. And we have to do some Bayesian inference in here. Now, in the first part, we were looking at using satellite images. Satellite images, you can see where's the oil, you cannot know the concentration. So what we're trying to invert is the location of the oil, not the concentration of the oil. And there we have to go to some distances comparing, not concentration, but the distributions, the location. And we use different distances, and the best distances we found is the W2 distance, comes from optimal transport, but it's computationally very heavy. And what we did lately in a paper, we replaced this with the artificial networks that get us more or less the same inversion, but in seconds. So, you know, this is just an example. If you have an image of the oil after 5 days, you know, so we're inverting for the location and for the time. Can we get the location of the time of the spill based on, this is a simple example based on an image of the oil. And so while looking with a Bayesian inversion for the time and the location, we will see it happened at day 7. And when we match it, we get the location of the oil very nicely. The distribution picks, you know, points to the location and the time of the spill. Now this becomes is heavy computation. We cannot do it real time on the machinery. And what we were thinking, some of what we're trying to do is, can we use some surrogates instead of the oil spill models that takes time, if you want to do it real time, to make it much faster. And the idea was to use some surrogates, polynomial chaos, to approximate the likelihood. But with the shape of the oil and it can split, the likelihood was quite unsmooth. And even with 100 samples, we were not able to fit the likelihood we're seeing. So what Samah did, instead of fitting the whole likelihood, the idea was to fit locally and iteratively. So every time we have a distribution, we sample from it. And we use the surrogate, we compute a surrogate. From the surrogate, we do a Bayesian inversion very quickly. We get a new distribution from which we sample, and we do that iteratively. And the goal is just, I'm interested in get to the distribution, you know, to approximate locally. I don't care about getting the whole distribution. I'm looking for the posterior. And red is massive sampling, and you know, in this, if you can see them well, these thin curves is the iterations while getting to the right distribution, and it works actually with the PCs if we iterate on that. And the if I remember correctly, it's 100 folds faster than the regular MC. The only issue we're seeing is that, you know, we're not able to push this to the real system because it depends on every location, and I'm not sure, you know, we're not sure how to do it. One surrogate that works for all the location, because, you know, you need to build a surrogate for every location. So we're still not sure how to push it to the real system. This is from the you know, from advancing the capabilities of the system and trying to give it more capabilities. Now, on the other side, we're working on the improving the data estimations and forecasting skills, and we're working on several directions. We're going to couple data estimation. It's a pretty tough problems. You have, you know, different scale between the ocean and the atmosphere, and the data in the atmosphere will affect the ocean. We're working on that. I will not talk about it today. We have for example, another publication that came out in QGRMS in last month, and it's about, but it's more on we're looking at it on the subseasonal scale. We want, you know, in the seasonal subseasonal scales, they put parameterizations, stochastic parameterizations in the system. But the way they perturb in ECMWF is just randomly. You know, once they put the parameters, they assume some range and they perturb, and some distribution. We're trying to estimate the distribution of these parameters with the data online. And there is an algorithm in which we used variation Bayesian to estimate the state, deterministic parameters, and the distribution of some stochastic parameters in the system, so we can tackle all kind of unknowns in the system based on the data. The last part is I will talk a little bit. I have two applications I will show on using AI how we can exploit this advance in the AI in our system to make it more efficient and more efficient. This is I would call this AI for the young people. I still don't understand very well the language. We have a very smart Abed student working on AI, and he's my advisor in AI actually. And we're using it. I will show you two applications and I'll stop there. The first one is to give you an example why this is very important for us. When I showed you that we're using the uncertainties in the ECMWF in the atmosphere to force the ocean, we have 50 members from ECMWF, and soon they will become 100 members from ECMWF. We cannot downscale these. It's too expensive for us. So what we do is just downscale the mean, and we add the uncertainties from the coarse resolution we have from ECMWF. And we have a lot to gain in the Red Sea if we are able to bring the resolution also of the atmosphere to the local scales of the Red Sea. So the idea here, can we use AI to downscale ensembles, large, massively? And so I'm not sure if you're familiar with TT, with Dries' work on CDA, continuous data assimilation. And basically, in a few words, continuous data assimilation is, I tell Dries, we should not call it assimilation, it's more downscaling. If you know the solution of the Navier-Stokes 2D on the nodal points, you can recover insights through some nudging at the large scales. Okay? And he shows convergence, exponential convergence. So you can go from the coarse to the high just by nudging at the large scale. And the theory is there. And he shows also that there is what he calls an uplifting function from the coarse scales to the high, to the fine scales. And the idea, but we don't know this function. So can we get this function and approximate it through AI? And this is what Abed did in last year, and he applied it to the Raleigh Binar. And so he used a 3D unit plus a multi-layer network. So basically, the coarse scales, the network is formed from coarse scale information that come to the 3D net to extract the features. From the features, you get to a latent space, and from the latent space, you apply a CNN in there to predict at the high resolution scale. So the thing of using CDA in here, because people, what they do from coarse to large, they run coarse model, they run high resolution model, and then they look in between. But these two are not consistent. Because if in the ocean, if there is a cascade of energy from the high resolution scale to the coarse scale. So if you run these separately, there is no consistency, and your network will not be the right network for the coarse scales of both are not consistent. When you put CDA in between, these two are very consistent, and this is the right way to do it. And this is the way it happens in practice. In practice, we have coarse scales constrained by data from ECMWF. Using CDA, we go to the high resolution scales that are consistent, these two, and then we apply this AI, downscaling AI, and you can do it very quickly. And we do it with a turbulent model with Raleigh number 10 to the 6, and it recovers very nicely, and the convergence is very fast. Here, when we put the data at every 8 locations and every 8 time steps. And CDA, the C comes from continuous, so the data are available every time. Now here we're pushing the machinery. We're trying to see what happens if I don't have the data every time, and still it works. So, if we have a lot of data every 2 steps, it's less than 1% the error with the network. If we have every 8 steps, we're still at 4%, which is still quite acceptable for us, especially we want to use that to represent uncertainties, not to downscale the mean. The mean, I will still use the physics. But it can be very nice machinery to downscale uncertainties, and the 4% is uncertainties in the uncertainty, so it's okay. The last step I will talk about, I tried to understand what's going on yesterday night, but I still don't understand it fully. And it's about, let me remove this. Sorry, I just saw it. Using reinforcement learning, to do data assimilation. I'm not sure if you're familiar with the word. I'm not. And this is what we've been working on for 6 months, and I try to understand the big picture. I'll try to tell you what is the big picture here. In the eNKF, we assume Gaussian prior and Gaussian likelihood, and so that I can compute a Kalman update. As a Kalman update is from the forecast, I just have the Kalman gain. It's a linear update of the innovation data minus forecast. Okay, and this is a linear. It's a matrix K Kalman gain. This is because everything is Gaussian. Now, what we saw from reinforcement learning, what people are doing, they use it for robotics, so robots can learn from the data and learn from their mistakes. They use a very similar expression, but instead of this linear function of the data, it's a nonlinear function of the data and also of the previous state. X dot is the derivative of x, so it's a right-hand side of the dynamical equation, dx dt. And so they train the system with the incoming data to get them f. Okay, so there is a language I really don't understand. I'm trying to understand from the AI community, these young people. So there is an agent making a decision, and when the data come, he looks at the data and see if I made a big error, I make a decision and I learn from this error. And basically what's going on, the networks we are using, I still don't understand very well how the mathematically network works, but they are estimating a distribution from which this update is sampled. And it's also stochastic. Okay, and you get updates that are nonlinear of the data. Okay, Abed will definitely be able to explain this better than me, but again, we're learning from the data as we go, and we're learning a distribution of corrections. And with GPU, the available machinery is very, very fast. And so we were trying this with the Lawrence 96. So there is a distribution, you start from distribution, you sample, okay, and you run your model, and you have the innovation, and by innovation, you make a decision, and you're learning from it. So a network learning the distribution of the correction based on the maximum entropy criteria. Yes, yeah, but the update itself. Now, what I like about this also is here, we have what we call a dynamical inconsistency in the Kalman update. It's linear. Okay, I was discussing with Abed to remove this, even remove the XF from here, and put some physics informed neural network on the PDF. So our update is dynamically consistent. So inform physics on the update. This would be pretty cool if you can do that. So this is the Lawrence 63 model, and we applied it comparing this RL with the eNKF. So in the Gaussian setting, both of them works pretty well. When we have non-Gaussian log normal observational noise, Kalman ensemble Kalman breaks up completely, but the RL is much more robust. This is very, very preliminary results. It's not published, it's not there yet. We're still doing more experiments, but we're so far I'm pretty impressed of what this machinery can do, and it's very fast. But we still need to understand the theory behind, but it's a different model, different way to look at the problem, and it would be very nice theoretically if we can make the links between the Bayesian inversion and this, but it's a different stochastic model if you want there, but the machinery seems to be much more robust than any eNKF, simple eNKF. I think this is it. So summary, we are building the machinery, but we are also trying to advance it as much as we can in terms of coupled assimilation, including uncertainties, using the uncertainties, and full coupling, and also add more available machinery. I think I'm not sure, I didn't track the time. Thank you very much. I hope I'm on time.
Thank you, Ibrahim, for that very nice talk. You're under time, so even better. Do you have any questions for the speaker?
Thank you very much. So first question about digital twins. It's people speak about this. Is a digital twin of Red Sea, or if not, what is the difference between this model and digital twin?
So digital twin is used for many things. And Aramco, they called me 3 months ago, they want a digital twin. And it turned out to be a harmful algal plume detection real time. So anything that you turn it from environment, from a real to algorithmic with some visualization, people are calling it right now digital twin. This is, I call it virtual Red Sea. It's a digital twin of the Red Sea. You call it, but also there are digital twins of, I'm seeing like from the electrical engineer from 3D city, but without the environment. So once you include the time varying dynamics, and there things become much more complicated. So even also the, I've seen digital twin of KAUST, where they do the building in 3D and some networks inside, but it doesn't include the varying real-time environment. So anything that is modeled with some 3D visualization is now people are calling it 3D, digital twin, but call it whatever you want.
But this question is connected to next question. I got impression that you try to model everything, but for me, for example, would be interesting temperature tomorrow in Tuval region. I'm not interested in what is in Africa coastline. So, and I think local models could be more accurate than your model because your model has much more uncertainties.
Mm-hmm. So now it depends what you do, but at the end you cannot model the temperature in Sewell without knowing the temperature around, right? You need the boundaries. So I can show you a simulation of KAUST campus at 2-meter resolution, but what's conditioning the KAUST campus weather is what's happening on the boundaries. And if you don't get the right boundaries, if you don't model what's happening in Africa, you will not get the right temperature in Sewell. It's not like independent temperatures that you can model it locally. And so I want to go to Sewell only, or I want to go everywhere to 2 meters, but I cannot computationally. So we do it by embedding domains 1.
But this multi-scale people like Yalchin Efendiv and so on, they
they do that on small problems.
Conditions,
yes,
some fake boundary conditions and so on.
You need to put right boundary conditions. Mathematicians assume boundary conditions. Once you want to go to a realistic system, you need real boundaries. You can assume, of course, and to do some theories in there, but you want to go to a real problem, you want real boundaries, especially when you go to small scale. Now we try to push the boundaries as much as we can, so even if the boundaries are not perfect, it will not affect less my domain, right? And that's why we go to Africa. I cannot do it only on the Red Sea because I need a buffer zone because my boundaries are still at 50 or 100 kilometers, and we do it. How do you call it? Multi-resolution, multi-steps. Okay.
And sorry, in the last question.
Yes, please. No, go ahead.
Somehow you model everything: salinity, temperature, and so on, pressure, maybe velocity. But if I'm interested only in velocity, maybe its model would be much simpler than your model.
So you can do shallow water for the velocity and the pressure and the height of the water, but it's an approximation, right? You're doing it on a shallow water. You're integrating vertically. But if you want to get the right velocity, you need temperature and salinity because of the geophysical, I forget the word. I'm sorry. Yeah, there is a coupled system. The velocity will depend on the density of the water, right? And it's very much driven by salinity and temperature and by forcing, and they are all together.
Good, thank you very much.
Okay, so you have to put it if you want a realistic system.
I think we've got time for one more question if anyone wants to. Yeah.
Thank you very much. Fantastic and inspiring talk, as usual. So, quick question. I mean, part of the thing that you said at the end that caught my eye with this, how do you ensure, or what do you mean actually by ensuring dynamic consistency in this kind of reinforcement learning update, because it is instantaneous, right? So one can think, for example, of trying to preserve some properties that are like, I don't know, if you will have, say, incompressible flow, you can still project on something that is incompressible at the end. And even in that case, you can still have a probability distribution over the fields that are incompressible, right? And things like that. But dynamics means time, right? So what do you mean by
this is exactly, how we try to do it from a Kalman point update. Once we have the Kalman update, we try to project it on some dynamics. Okay, but then once we have a distribution, we don't know how to project it. So we usually project the mean. Okay, so it's cooking a little bit. Now, what I'm thinking that, if we remove the XF from here, there is no reason why we have this XF in the network. And when we train the network F, the sample, this network is physics informed network, what they call in the machine learning community. So they can train while there is a condition on the physics, and we can put some physics in there. And in the machine, they can include it and train the PDF directly with a physics condition network. This is how I'm thinking.
Okay, but what I was thinking, and this was my question, right? When you do an update on data, essentially from the physical perspective, there's no time that it has elapsed, essentially.
True.
So if I can think of imposing, say, I don't know, incompressibility or some kind of conservation, right, and bring it back to that manifold, and that is okay because it is instantaneous, right? No problem.
I see what you mean. But the others is more complicated, but here I have also the time derivative. I have the time derivative in the network.
Okay, so in that case, you will be a time derivative that is tangent to that manifold or something like that.
I could in this situation, not in the Kalman situation.
Yeah.
And this is how I'm thinking.
Okay.
So this model seems to provide a nice framework.
Exactly. So you
then
exactly. You should kind of be in that manifold.
Absolutely.
And each of the samples should remain in that.
And this model might give us this way to do that. It's pretty cool. There are not, according to Abed, there are not many people working on reinforcement learning. It's very new. No one in KAUST is doing it yet, and it seems that it's a very interesting direction. I'm sure, if it works well, it will open a lot.
And the other things that you mentioned, also the low rank updates and the localization, that is also very, very nice. I mean, it comes directly from the low rank that you're doing. But if you do sort of hierarchical approximations in the forcing, in the ensemble, right? I mean, multi-level type of things, they immediately raise the dimensionality a lot, and you diffuse this is
something that needs to be tried.
With this localization, this could be used.
And doing it from the atmosphere and do it on the ocean and see the impact. Absolutely.
And the other thing that I'm interested in is this optimal control for the booms that you mentioned.
This would be super cool. If there is something to do that, and also the optimal control, optimal pathway under uncertainties. So a ship want to go, and Aramco is very interested in that. I want to go from this location to this location with the least footprint of carbon. I want to reduce, I wouldn't want to use less carbon. I want to use less carbon.
Definitely.
And if we can do that real time, there is a big, it's also a global problem. People want to reduce the CO2. That would be very cool.
Okay. Great. Thank
you
very much.
Sure. Thank you.
Okay. Sorry, so you wanna finish?
Go ahead, Hamza, please.
So just a comment on you mentioned the particle filter. As we know, the standard particle filter doesn't work in high dimensions, but it has been a lot of research in this area trying to enhance this. And actually, I work with AJ on this, and we have a recent preprint where we actually run data assimilation shallow water at 10 to the 5 dimensions. And I compared it with ensemble Kalman filter and these ensemble methods, and our method runs much faster. In fact, so the simulations on my machine, where it has 26 cores, takes about 8 hours.
How many particles are you using?
I use 1,000 particles, but still, if you want even the ensemble Kalman filter will not work because the number of data. The dimension of the data is very small compared to the dimension of the state. It's only 24 data points compared to 10 to the 5.
Okay.
So my question actually about the data, what's the dimension of the data compared to the?
It depends on the problem. In the Red Sea, as you know, most of the data coming from surface, so it's along tracks, and there are not many. Now, when you go,
Can you give me like an approximate dimension?
If on top of my head, I don't, roughly speaking, you're getting 1, 2, 3% maximum. Now, but again, don't look at the dimension in terms of numerical dimension. I mentioned the physical dimension. So one data might give you much more information than, it's not numerical. Now, to go back to the 10 to the 5, this is with the Lorentz, with the shallow water. 10 to the 5 for hours is another dimension.
Of course, but then you look at the number, right? The dimension.
When I said that I'm not a big fan of particle filters, and I meant it, because if I want to use the 100 particles to approximate a distribution in the dimension of 10 to the 8, 10 to the 9, that's what people are trying to do. I don't see how you can approximate a distribution of 10 to the 8 dimension with 100 order of 100 particles. This is our
this recent method.
I mean, just from a pragmatic point of view.
Well, this recent method actually
it's not a good approximation model. This is what I meant. But of course, and we do it. Gaussian mixture, particles. We definitely beat the curves. This is not a mystery.
So what about this recent method? We compare the accuracy. So for a fixed accuracy, our method is much faster and it's much better.
It's 10 to the 5. So the only difference I'm seeing in particles, I don't know what you're doing in particles. There are many methods, but there is a Kalman updates. You have a linear updates.
Yeah, of course we know. It's no linear updates. So we talk non-linearity here. So
but you still need to. The bottleneck in our science is to update, to propagate, to forecast 10 to the 5, 10 to the 6. This is no way. Because every model takes around 4,000 cores. If you 10 to the 5 in a small problem, you multiply this by 4,000 cores.
It's a different, we do it in a different way. But,
but you still, I'm not sure what is your different way, but you still need to forecast with your model, right? Unless you do a neural network or whatever, which I don't believe they can represent all the dynamics.
We don't have actually matrix multiplication, matrix inversion. It's very different from ensemble method.
You still have the forecast step, right, or not?
Yeah.
Yeah, so the forecast step, you have 10 to the 5 particles that you need to forecast with. This is the bottleneck.
No. We don't have 10 to the 5 particles. You have a vector 10 to the 5. That's the state, right? Just 1,000 particles.
So you run with 1,000 particles?
Yeah, 1,000.
Yeah, I still find it hard to believe that with 1,000 particles, I can well describe a probability distribution with large dimension.
I mean, there has been a lot of research in this area, but
I know, and we're trying a lot as well. But I'm telling you, just from a pragmatic point of view, from a model, approximative model point of view, I don't see how we can use 1,000 particles to describe a full distribution that is very non-Gaussian. This is my point. Maybe I'm wrong.
As I said, there has been a lot of research.
I know.
A lot of effort, actually. Yeah.
Good.
So thank you again for the nice talk.
Okay, so we'll conclude the talk again. Thank you very much.
Thank you.
Thank you.
Sure. Concerning the live streaming of simulation parameters. Concerning the live streaming of simulation parameters, how far are you in that work? Maybe you can utilize the Catalyst library, which enables live visualization without I/O bottleneck and also stopping simulations, changing parameters and start running from their own.
Can you, at the beginning, concerning what?
Concerning the live steering of simulation parameters, how far are you in that work? That's what the question says.
Live steering?
Yeah, you can click on the chat and you will see immediately.
But I didn't understand what is meant by live steering.
Can you hear me?
Yeah.
Yes,
you
please go ahead.
Really?
Yes, okay, thank you. I want to ask because at some point I think you discussed that you wanted to change the stochastic parameters during simulation. Was that correct, or did I
for the online, yes. Please tell me.
The question was how far you are in that work.
Actually, the paper is published. You can look it up. It's a QGRMS. I'll be happy to send it to you.
Okay.
But it just came out last month. So we're trying to estimate, the distribution of the stochastic parameterization inside the system online within the filtering process.
Okay.
Okay.
Cool. Yeah, sure.
Thank you.
Thank you.
All right.
Okay,
this time
good.
we'll
Thank you very
Thank you
much.
very much, Ibrahim. Thank you.